The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Where the probability of flipping heads is p. And if you flip it a few times, so you get heads, tails, heads, heads in a row, you can convert that into a binary number, 0.1011. So say that heads, tails, heads, heads goes to 0.1011. And for any flip, like infinite flip of these, you can get some binary number, right? So we define the function, or we were told to define the function fp, given the probability of flipping heads is p, of some number between 0 and 1 would be equal to the probability that a random infinite flip of this unfair coin will give you a binary number less than x. So and so we went ahead and proved some things about this function. So in the case where p equals 1/2, the function is really easy. It's just going to be the x equals y. But for p not equals to 1/2, we have this wacky function which we know it's increasing everywhere. This is pretty easy to see just because if x is greater than y, then you're more likely to get a flip that's less than y than less than x. That's less than x and less than y. Right, so it's going to be increasing. And we showed that it'll be continuous, but we also showed that whenever it's differentiable, the derivative would be 0. We showed that the arc length of the function would be 1, or sorry, it would be 2, again, unless p equals 1/2. So it's going to be this really weird looking fractal, which will look something like this. You can kind of approximate it. It's going to be kind of have some lumps peaking in the middle, and then smaller lumps peaking at 3/4 and 1/4, and then more and more smaller ones at all of the rational numbers where the denominator is the power of 2. The dyadic numbers, yeah. And when you keep ending this, and you get you get the function I'm describing.
So your results are that it's continuous,
Yeah.
no matter what p is. I guess p had better not be 0 or 1.
Yeah. For p in 0, 1, non-inclusive, p not equal to 1/2, we have f of p is increasing, continuous, we know that it's not differentiable at the dyadics because it'll always take jumps of dyadics, so it will be continuous. Proved in more rigor in our paper. If it is differentiable, the derivative is 0. We know that f of 1 minus p will be a rotation of f of p by 180 degrees. We know that the arc length is 2. do you think I'm missing? We know that it is differentiable somewhere, in particular differentiable at the point 1/3 among many others. But this is like, we can show that it is for sure at this one point differentiable. Anything else? So should I be proving things, or do you want to know what we
No,
did?
this is great.
Okay.
This is just the debriefing. It's just what I wanted to hear about it. It's actually, so I have the advantage that I worked with you on this project, so I know a little bit about it.
So one more thing. And the integral from 0 to 1 of fp is equal to 1 minus p.
It's a pretty weird function. When you first plotted it, didn't you? You came up with a
Yeah, we have pictures of it as well.
picture of it. Were you surprised to see it was different? It was smooth? I mean, that it was continuous when you plotted it?
No, I think we already had proven that when we plotted it. It's more showed us how this helped, at least it helped me thinking about differentiability a lot. Because you could really see that it made these jumps at the dyadics. And it helped me see just kind of how it changed for different values of p, because we saw that when p got smaller, it did the same type of thing, but getting closer and closer to 1. And it had the jumps in the same places, which is really good to see. But you could see it getting bigger. But also, I guess, yeah. And you could also see really nicely the rotational symmetry of p1 minus p.
Which could be written as a formula in terms of, like it's 1 minus.
Yeah, you probably say
1 minus p of x.
f of 1 is what? 1 minus fp of 1 minus x. Is this right?
Yeah, I guess so. So actually, not everything that you said here on the board is in the paper.
Well, we should probably fix that then.
And yeah, I would. So now begins a process of revision of the paper, and I think it would be great if you could add some of this to the paper.
Yeah, sure.
Like the integral thing isn't there. I think that the statement that if it's differentiable, the derivative is 0 isn't
Right.
there.
And also that it's not differentiable at the dyadics.
Yeah,
It's
and
not
even
there.
that's right, exactly. That's even more somehow a bit, yeah, they're both important.
Yeah,
So-
for sure.
But maybe we should talk about it, a little bit of it now as well, of the comments. You guys have to choose between digit and bit.
Oh, okay. That's probably my fault, because I was using bit sometimes.
So digit refers to your fingers, and there are 10 of them. For me, bit is more natural, but you can choose either one, but you should stick to it through the paper.
I have no preference. I'm fine with that.
When?
I'm fine with that.
It's sort of the same with an introduction. I think it's great to put these pictures in an introduction. And there's a nice argument for putting a specific calculation in there. I'm a little bit of two minds about that, because it gets into the detail a little bit more. There's a parenthesis missing here.
Yeah.
But just giving the sense of how you compute these things early on. When I first saw this function, I thought, what in the world? But then actually seeing the computation makes it much clearer what the function really is.
Yeah, I agree.
And seeing that it comes out as a rational function of p is kind of cool as well. I guess it's always a rational function of p. So you get some strange collection of rational functions that appear as the values of this function, depending on p.
Yeah.
Kind of odd. Kind of interesting family of integer coefficient rational functions.
Is it always going to be
I
a
think
rational
it's gonna be
function?
rational. Yeah, I think so. Just that's what the functional equations tell you. So there's this
Or if that's for rational numbers.
for dyadics.
Or for dyadics, yeah.
Right, it come
Yeah.
out that way. Well, that's what your calculation illustrates.
Thanks.
What do you think of having AKA in a math text?
Oh, is that?
It's kind of, it makes me think of crime dramas or something.
Well, I was also having that picture in my mind when I wrote AKA the staircase.
I got the right image. What do you think of that? Is it stylistic?
It didn't bother me when I read it. I think that if the math is solid, then there is some leeway to be a little bit informal in the writing.
And be a little humorous. I think so too. This, I think AK occurs once and maybe twice more in the paper. than-
At least once more.
Yeah, so
on
maybe,
the last page.
maybe back off from that a little bit.
Okay.
Was he like also known as or something? Is that?
Well, or yes, or which we, I'm not sure how standard it is, but you could say which we will call dyadic rationals or something like that. Make it clear that in this paper, that's what the word terminology will be.
I really liked how the example in the introduction was carefully chosen to work well later in sections 2 and 3.
Huh. So you'll see a lot of commentary about this. There's a lot of times when I read these papers, what I get is the sense of the author working his way through the project, and there's a certain attraction to that as a sort of journal. It's almost a journal. It's not actually the way math papers in math research journals appear.
Mm-hmm.
It's very interesting. It's especially true in Michael's section of the write-up. For example, the word "then" occurs quite often. Like you're going along, then you do this, then you do that. There's a sense of a temporal progression somehow through the paper. Whereas in the math journal, those thens would typically be replaced by thus. Do you see the tone difference in tone? It's more of a sense that there's this piece of mathematics that's there, and you're going through describing it. You're not. It's there without time. It's there permanently, and you're describing it. Whereas when you say then, there's a sense of progression through it. You see the difference in tone?
Yeah.
It's quite subtle, but I'm very struck by it, especially in Michael's section. But it's true in other parts as well. To a certain extent, I think it's attractive to have that sense of movement. It's just a little non-standard. What do you feel about that? Did you pick that up also?
Well, that's very similar to the use of future tense, will, and present tense. Present tense is much more common in mathematical writing for the same reasons.
Mm-hmm. So it's risky to do that because it's harder to keep the reader situated. If you have the sense of progress, then there's a sense of mystery about what's going to happen next and sort of where you're going. Whereas if you have the more static perspective, it's easier to situate. It's easier to give guiding phrases to say where you are.
And that makes it easier for the reader to follow what's going on.
And that makes it much easier. That makes all the difference in reading a paper. Or for that matter, giving a lecture. If you give a presentation and you just head off in some direction without telling the listeners where you're going, it's quite uncomfortable. So that this occurs here as well in other places in this paper. Like for example, in the differentiability section, differentiability of the third. It begins by saying characterization of sets on which FP is differentiable is not available yet. Well,
You mean about it existing?
yeah, I mean, maybe somebody knows. Not available to you yet, I guess, you could say. But it's a different field. In fact, I felt what I'd really like to do, I felt that this is about the fact that it is differentiable in the third, and that's the thing to lead with, rather than what we don't know.
Yeah.
Although actually, perhaps the thing to lead with would be the fact that it's not differentiable to the dyadics, and then you could lead into...
Oh, that's great.
Yeah.
So that would be a good place to, that's a more complete result, and that would be a good thing to lead with. That might be a different section. I wonder, in fact, later on here in the section on arc length, there's this amazing formula for the, so he has these, I'm looking at Formula 9. He has this is Michael writing, he has this formula for the difference between the value of f at two successive dyadics. You have a specific 2 to the minus n in mind.
Yeah.
And it's given by this cool product. That formula might be useful in other things.
Yeah, that's how I would do the dialectic.
And so one could break off the derivation of this formula.
Dump on top, and the
Put
first
it-
thing that happens a bit later.
Put it earlier, and then have that available and have this section just refer to it. Because there's plenty more. I mean, he uses Chebyshev and things. There's plenty more in this section. And it would make sense to me. I think this is a very cool formula.
Yeah.
And it's useful. I think it might be useful in improving non-differentiability. I think I'd suggest that you might have a section after the introduction which sets up some of the simple properties of these functions, like give an account of the functional equation, and then as an application of the functional equation, you have that integral that comes right out. That might, if you see a place for it, it's nice.
The ones that were in the continuity course?
Yeah, I think some of that could be pulled out as a separate. I can't remember what I suggested here, but maybe that's right.
Okay.
So good. And then there's the end thing where you talk about three-headed coins. I think that's pretty cool, and I definitely think the Devil's Staircase is awesome.
Yeah,
Thing to end with.
yeah,
Did you like that too?
yes.
But it needs a reference.
Okay.
What other comments, Susan?
Just to go back to emphasize for the way that you present, the way that you present the proofs. Currently, you're sort of having a logical flow, and then you have the answer, and that can be difficult for the reader to follow. So I suggest using theorem proof format so people know what you're proving as you're proving it. And even within the proofs, if you have subclaims, say what it is you're proving before you give the reasoning, so that people know what it is you're proving, why you're giving the statements you're making. If it's really straightforward, like only a sentence or two, you might not need to do that. But if it's more than that, it can be.
Wait, what's a sentence or two?
A subclaim, the reasoning for a subclaim.
Yeah.
Did you know each other at all before?
No.
Did you know Michael before?
No.
Did you know Michael before? I think you guys have done a great job in forming a team from scratch, actually. And it's, I hope we keep it up. I thought that pulling this together like this, it's really very good.
I'm impressed by
And-
his paper. I'm impressed by how well it works as a whole.
Mhm. Mhm.
It almost looks like it was written by one person, which is the goal.
Mhm. And I think each of you supports the project in different ways, so it's interesting collaboration. Every collaboration has different aspects to it. That's one of the fun things about giving this course, is you see 9 completely different forms of collaboration.